Introduction to LANs. So, as I previously mentioned in the last model, LANs communicate at layer 2 of this thing called the OSI model, which we're going to dissect here in the future. But how do they do that? A lot of people are getting, if you're in networking or you're getting familiar with networking, you probably heard of an IP address. IP addressing is another section that's coming up here in a little bit. And a lot of people think IP is all there is because that is the predominant protocol that connects us in the world. However, or the prominent layer 3 protocol that connects us in the world. But however, LANs actually communicate at layer 2 before IP ever comes into play. And there's many different protocols that run at layer 2 of this thing called the OSI model. Okay, so let's say that I have two computers here. You know what? I might actually have already put this on the next slide. So let me, okay. So let's talk about this thing called a MAC address. Every computer or network device that's an Ethernet or a WLAN capable device, that's either wired Ethernet or Wi-Fi device basically, will have a MAC address at layer 2. Now this MAC address is burned on from the manufacturer and they're designed to be globally unique, okay? So for example, these addresses here that you're seeing, they can be represented in a couple different ways, but there's two portions to this MAC address, okay? It's a 48-bit hexadecimal address, okay? The first 24 bits is what's called the OUI. It's an organizational unique identifier, okay? And so you get address pools that are assigned to manufacturers of networking equipment. They get a pool with the first 24 bits, and then they use the second 24 bits to uniquely identify every network interface they put out there. So if you look, this is the back of a phone. We have a wired MAC address for the wired adapter in the back of the phone. You can see that's 802.3 MAC address. And then over here, you've got an 802.11b MAC address, which means that it's a Wi-Fi MAC address. Okay, 802.3 is the IEEE working group for wired networking and Ethernet. 802.11 is the IEEE protocol for Wi-Fi, okay, or WLAN networking. Now, this 48-bit hexadecimal address, again, there's two parts. The first 24 bits is the organizational unique identifier, and that's actually how we can run some tools to discover devices on the network and say, oh, that's a Cisco device, or oh, that's a that's a Brocade device, or oh, that's a HP device, or whatever it is, right? Tools we have that will run queries to detect the type of device, and one of those things is based off the MAC address, and every computer has one, okay? So and let's go back to this for a second. One thing that would be interesting for you to do is to figure out what your Ethernet MAC address is. So I believe I had this to run as an example later on, but we'll go ahead and just do that real quick. So let me bring this window into view, and we're going to do open up command prompt. So go to start and run, type in CMD, hit enter, and this is what comes up, okay? Now from here, we're going to use a utility. I'm sure you've heard of it, but if you haven't, you're going to use it many, many times in your network career. It's called ipconfig, and we're going to use a variable with that, okay? So we're going to do the / and type all. Now, I have a lot of different networking devices in my computer here. In fact, my computer I think had 4 NICs on it from the factory, so it's got several, or might have 2 or something like that. So we're going to look here, and my current adapter is the wired adapter. So if I keep going down here to my Ethernet, I bet you it's this one right here, Ethernet adapter 2, and if you look right in here, there is the physical address, okay? So we could see 64006A, that portion would belong to Intel. Even though my computer is a Dell Precision Workstation, it has an Intel chipset. So Intel was actually the one who made the networking adapter in the computer, and therefore I have a physical address that would be assigned to Intel. In fact, if we wanted, remember I said we could look this up. I'm going to see if I can open up a browser and keep it in the field of view here. Let's see. And what address do we have? 64006A. So we're going to search MAC address 64006A. And if we look at just the first thing that comes up, oh, well, never mind. It's Dell. This is actually assigned to a Dell device. So it could have been from the Mac pool, because even though Intel made the chipset, it could have been from the Mac pool for Dell. So that's interesting to find that. And there's lots of different tools that would show you this. Okay, so if you look up you can see there's a few different ones. So Dell is where that MAC address was assigned. And they were assigned anything from 64006A alpha, and you can see that last 24-bit addresses, all zeros are all Fs, which means they could assign any of those addresses, right? So that's how to find your MAC address. LANs communicate using layer 2. That means they communicate using these MAC addresses. Whenever I want to communicate with a host on a LAN, I'm going to communicate by finding their MAC address and sending a frame to it. So again, I know some of these topics we're talking about, you're not going to have a great understanding until we get through a couple more chapters. But just try to remember the key things I'm explaining, which is LANs communicate at layer 2 of this thing called the OSI model, and we use MAC addresses to communicate. Now, at layer 2, the type of traffic that we send on a wired network is a wired Ethernet frame. Okay, so this wired Ethernet frame is a well-defined frame, and there's two key components to it. One is a destination MAC, and the other is a source MAC. Okay, so then you've got a type, and then you've got a data portion of the frame, and then you've got a frame check sequence. Now, the big thing in this, again, this is for wired Ethernet networks, is that I have a source MAC that defines who is transmitting on the network, and you have a destination MAC, which is who the traffic is for. Okay, so it's like sending somebody a postcard, right? I have to know their address to reach that person. So if I don't know their address, we can use a particular protocol for that. Okay, it's a very useful protocol, and it's called ARP. ARP is Address Resolution Protocol. Okay, so if you want to see all the stations that I know of on my LAN, then I can go back to my command prompt. So go to Start, Windows, and type in CMD and hit enter, or you could just follow along with what I'm doing, right? You should be able to see all of this just fine. Let me get rid of some of these annotations, and we're going to use the command this time, ARP-A. So I have different networking adapters on my computer that I've already mentioned, and this is my main adapter right now, that Ethernet adapter. So you can see that there is some static things down here, and we will get into this later, but that's basically a broadcast, all Fs, and then a 255 octet. That's a broadcast address. That's how we can reach anybody listening on the LAN. And then we've got some multicast stuff down here. Everything above that, this 254 to 1, are addresses that I had to learn through the ARP process. And you can see that because they are dynamic entries, which means they were learned as I had to communicate with somebody. So, do two stations on the same LAN know about each other? And the answer to that question is, it depends. Best technical answer of all time, right? It depends. The answer is they do not by default. They would have to resolve each other, right? They would have to learn about each other. And we can use the ARP protocol to do that. Now, this is where we do use IP, because TCP IP. because I need some way of communicating with the device to learn about their layer 2 address. Okay, but on LANs we do use layer 2. Okay, so let's say I know there's another device on my LAN, and I know the device has an IP address of 10.100.110.2. Okay, I know that that's there. So if I bring this window up so you guys can see it a little better here, just put this in here, and we ping that device 10.100.110.2. Now notice up here in my entries, there's no mapping for 2. Okay, there's no mapping for 2. There's mapping for 1, but not 2. So if we ping that device, maybe it was .3 I was thinking of. That could be it. Oh, no, there we go. There is a device at .2. So you can see I'm getting a reply. So this ping is a way to test network connectivity. Okay, and you can test, it's a layer 3 network connectivity tool, and we'll get into the ping command a little bit later on. But what do we really just do there? Yes, we tested connectivity to that device, but you notice this first packet failed. Okay, we sent 4 packets. See right here? Packet sent 4, received 3, 25% loss. Now, here's the fun part. If I start the ping process again, I'll get 100% success. See, packet sent 4, received 4, 0 loss. Now what that was, guys, that first packet failed because of the time it took for ARP to discover the MAC address. Let me say that again. The first packet fails on a ping so that your device has a chance to do an ARP broadcast, which is sent to all hosts that are listening on your segment, so that they can respond and say, hey, I'm 10.100.110.2. Okay, and we'll go over this process in detail. I understand some of the things I'm talking about are jumping ahead a little bit. It's just the way this first course goes. It's the foundation. So there's going to be all types of new stuff, but we will dissect each one in detail. Okay, so you noticed .2 was not in my ARP table up here. Right? It was a 22, but not a .2. So if we do my ARP-A command again, and we scroll up, check it out. I now know the MAC address for .2. Okay, so I had to learn it with that first ping, and then before I could send out a packet to the host, I had to learn its MAC address, and that's why that first ping failed. So ARP had to go out and learn the MAC address at layer 2. ARP is address resolution protocol. We're going to look at it more in just a second. And I sent this message to everybody on my network using this address. All Fs, all ones. Okay? And we'll explain all this in detail as we go forward too. So everybody on my LAN got a copy. And it said, I am looking for 10.100.110.2. Are you that person? And that's why I couldn't send a message that succeeded, because I didn't have this layer 2 address. Once I had the layer 2 mapping, every packet since then passed successfully. Okay? All right. So you notice in our example here, my source MAC was my source MAC, yes. But my destination MAC was all Fs. All Fs signifies that it's a broadcast frame. So this frame's going to everybody on the LAN. And we'll talk more about that in a moment. Now, the maximum payload, or MTU, is 1500 octets or bytes with fast Ethernet. Gigabit Ethernet supports larger payloads that are called jumbo frames. Okay, there's all different types of frames, to be honest. We'll get into some of that a little bit later. Okay, now speaking of types, you've heard me say broadcast traffic. Okay, that means goes to everybody. So broadcast is a type of transmission, data transmission we use at layer 2, and we also use it at layer 3 as well, but right now we're focused on layer 2, okay, that goes from a source to everybody on the LAN. So again, if we have a switch here, and I'm over here, and I've got 4 other people, if I send a broadcast, it's going to go into the switch, and it's going to go to everybody, right? Everybody gets copy. So I use that for protocols like ARP to help me understand your layer 2 addresses, okay? Now, notice whenever I did the ping that only the first ICMP echo failed, or the first ping packet failed, okay? That's what it's called, as ICMP echo, by the way. Whenever you do a ping, that's what it's really called. Now, the second one and every subsequent one was just fine. That's because I had the layer 2 addressing and I could send that frame directly. That type of transmission is called Unicast. Okay, Unicast is 1-to-1. So I was this host, and this host was the one I wanted to connect to. So the first packet went to everybody. I learned about host 2, and then I could send the messages directly to host 2. Okay, but any of my computing devices on my LAN is not aware that these other devices exist unless you resolve it. Or the other thing that can happen is it resolves you for some reason. If any other device connects to you on the LAN, you learn about their addressing that way as well. Okay, and there's a time limit. Those entries will expire over time. So it's something that happens every time you reboot your computer. You got to learn about different addresses, all that kind of good stuff. But it's a dynamic thing. It happens automatically. Okay, as long as you have an IP address and they have an IP address, you're both connected, circuits up, all that kind of good stuff. All right, and then we have a multicast transmission type. And this is all layer 2 and, layer 2, and it's also part of IP. I know that may seem confusing right now, but these are some different transmission types, and right now we're talking about them at layer 2, but we will also be talking about them at layer 3 as we go forward. So multicast is a little bit different, and we're going to dissect that traffic flow, and actually in just a second. I just remembered I got some cool stuff here for that. So Unicast, I am sending from 1-to-1, okay? So Blue wants to send to Hannah, and by the way, I'll go ahead and introduce them. I have 2 lovely dogs. One is a blue healer named Blue, a very creative name there. And the other one is an American Bulldog named Hannah, and she is freaking awesome. So some of the things will be named after my pets. Others may be named after my daughter. Others may be named after imaginary people. You never know with me. All right, so Blue needs to send a message to Hannah. And because Blue would already have Hannah's MAC address resolved, I can send that message out directly 1-to-1. So what does that look like? If you notice, my little ball there goes directly between the two, right? So I can send traffic directly between the two. It doesn't bounce back and forth. It's just, that's what I'm using as an example, right? I send a packet, I get a confirmation that the packet was sent, that kind of thing. Or Hannah could be contacting Blue, and Blue returned, yes, I got the packet kind of thing, right? Or the frame. All right. With broadcast traffic, though, this is delivered to everybody on the LAN segment, okay? And we'll talk more about what that means in a minute, but this is a flat LAN topology here. All devices are connected on the same layer 2 switch. There's no different configs or anything. It's all a flat LAN. Then whenever I send this broadcast out, here's what that looks like. I send the one message, which gets replicated to everybody on the LAN. Broadcasts get flooded out all ports except the port in which it arrived. Okay? And that's on a switch. If there was a hub there, then every frame would be repeated. Okay? That's something interesting I'll just say. If we go back to this Unicast transmission, let's say for a moment, let me just... So let's say for a moment, we have a hub here. Let me change my color here. Okay, so we've got a hub. And let's say we've got a couple other hosts. Okay. Whenever Blue sends that frame, it would actually get replicated to everybody. because that's what hubs do. They repeat the packet. They repeat that that code, that data. Okay. Switches, I can forward frames directly to other stations if I know their layer 2 address. Okay, so switches are much better than hubs, and we'll talk more about that as we go forward, but I just wanted to bring that up now. So again, broadcast, I send my frame, it gets replicated to all other devices, and on a switch, it's really just going to happen so I can learn addresses. That's what those broadcast messages are typically about. It could also be a type of traffic that I need to send to everybody, or I need everybody to hear. But a lot of times it's just about discovery, because it's much more efficient to not have to communicate with every host on the network every frame you want to send. Let's say I have 10,000 hosts on the network. Well, do I want to send 10,000 packets every time I send a packet? No. I might want to learn about the host I need to transmit to, and then I want that conversation to be just between us, right? I don't want everybody else getting a copy of that. Not only is it inefficient and creates way too much overhead, it's also a security risk, right? So multicast, is streamed across the network and allows subscribers to tune in to the stream. So this is a specific block of addresses that we can use to basically start talking on the network and allow other people to dial into that address, kind of like conference calling, really. So we allow other people to subscribe to that stream, okay? So if we look at what that looks like, we're sending out data, and everybody who subscribes is getting a copy. Now, it doesn't have to be everybody that I'm showing here. It could just be like 3 of the people that are subscribed, or 2 of the people that are subscribed, okay? But the point is that I'm sending data, and that data is getting, people are tapping into that stream to be able to hear that data, okay? All right, so LAN communication again. LANs communicate using layer 2, 802.3 based Ethernet networking, and that 802.3 thing, that comes from the IEEE, okay? The IEEE, I should go ahead and probably announce them. I'll go into more of what they do later, but it's the Institute of Electrical and Electronic Engineers, and they help create standards. Standards that can be used so that different vendors can design technology around a standard and know that it will be interoperable with other vendor solutions around that same standard. Okay, so cool stuff. And the 802.3 thing is the working group that defines wired Ethernet networking. So LANs communicate using layer 2, and it's based around this standard and its variants. Okay, there's plenty of sub protocols around 802.3. All right. So IPv4 we'd use to simply resolve your layer 2 address on the LAN. That's really it. Okay. Your IPv4 subnet mask, which if you've ever put an IP address on a computer, it might look something like this, like 10.1.10. We'll just say 20. And then below this, you would have put in a subnet mask, or one would have been given to you through a DHP process we will examine a little bit later in the class. So these are the 2 critical addresses to have on a LAN. This is your actual address. Okay, it's kind of like your phone number, right? That says we can reach you here. The bottom portion here, this is what's called a subnet mask. We're going to dissect all of this in a later module, but that identifies the network you are on, the LAN you're on. So, and we'll talk about how that all works a little bit later, but just know that identifies the network significant portion of your address, which means just like there was 2 parts to a MAC address at layer 2, where you had the OUI and you had the actual host ID, at layer 3, there's also a network portion and a host portion. So this mask tells me that this host is on the 10.1.10 network. That's the network address. And again, and my host ID is 20 on that network. So basically that mask tells me that I can communicate with anybody from 10.1.10.0 through 10.1.10.254. And again, all the mechanics of that we talk about in a little later module. It's another critical component of the class that I'm just bringing up super early, but hey, it's what we're doing. We're here to get dirty, right? Messy. All right, so we use ARP to locate machine MAC addresses we do not know, and we use broadcast messages to go out and discover or resolve those addresses. So we go out and send an ARP broadcast that says, hey, hello, I'm here. Are you this host? Because I'm looking for you and I need to send you a message. And everybody on the LAN gets a copy of that, right? Because that would be a broadcast message to everybody that's on my segment. And then hopefully that host responds and says, yeah, my MAC address is this. Once I have that resolution, I can forward out that frame, okay? If you want to see the computers or devices, the network devices that your computer is aware of, open up the command prompt, the Windows command prompt, start, run, cmd, enter, and type in ARP-space-A, okay? And that will show us a list of the MAC addresses that your computer is aware of. So you saw me do that earlier in the lesson, and let's get ready for the next.